Swayam Prabha. Digital India. Educated India.
This lecture is on frequency domain signal analysis. Like as I had told you before, in condition based monitoring, signal analysis is very important, and that too every machinery has a distinct frequency of operation. So, through the signal which has been obtained through the transducers, we need to analyze them to find out the characteristics frequencies of the signal, or in other words the signature of this machinery, because every machinery has a distinct frequency. So, how do we find out the frequency of that machine in a particular signal which we have acquired. So, in this class we will be going briefly into the mathematics of such signals, how through Fourier analysis people do determine the frequency components of a signal. For example, you all would recall in your undergraduate maths class on Fourier transform, the teacher would have given you many waveforms. It could have been sawtooth and square wave, etc., triangular, and told you find out the A, B and C coefficients, and then expand this waveform as a series of sums of sines and cosines. And in fact, this is the very starting point of frequency domain signal analysis, and in this class we will be focusing our attention into such analysis, and later on we will see how such analysis can be used to analyze real world mechanical signals. Well, as you all know, the need for frequency analysis is because of the fact that every mechanical component has a characteristic defect, a characteristic frequency or frequencies which could be related to the defect in the machinery. So, we will be having a distinct signature out of this machinery. This signature is its characteristics frequency. For example, if a machine is rotating at say n rpm, its rotational frequency is nothing but n by 60 hertz. So, if I have a say just a machine, maybe a shaft supported on a bearing, and this was rotating at n rpm, and if I had put an transducer here, okay, you all can appreciate the fact that in the time domain the signal obtained by such a transducer would somehow look like this, and the inverse of its time period is the frequency f is equal to nothing but n by 60 is equal to 1 by t, where t is in seconds. Okay. So, this is a simple signal coming out of a machinery. Well, if the signal is of this form, I can very easily tell the frequency is the inverse of the time period, and such a signal having just one frequency is usually known as a pure tone signal. But you will realize later on, you will see actual signals coming out of machinery. No such signal from an actual machine is of such a single pure tone. In fact, if you are to measure or record the signals out of real machineries, this could be of this nature: signal out of an actual machine. So, if I asked you the frequency of this signal, you all will be lost as to, well, how do I find out the frequency of such signals, because I do not see a distinct time period, they are randomly varying. So, this is the problem we have in front of us. How do we estimate frequencies of the signal? And obviously, this is not a pure tone signal, this is not a single frequency signal, there are many frequencies. The problem before us is how do I find out the frequency contents in the signal. So, that is what we are going to look into in this frequency domain signal analysis in machineries, and we will see how we can do that. Okay. So, because of the fact why again frequency domain signal analysis is important, because signature of a machine component is unique. Okay, when I am talking about, say, in a machinery, ball bearing, gear, pulley, impeller, etc. A rotating shaft. Rotating shaft itself can manifest in many ways, as an unbalance, as a cracked shaft, as a misaligned shaft, as a loose shaft, as a bored shaft. So, there are many ways. So, each of these mechanical conditions, be it a defective bearing, defective gear, defective pulley, unbalanced impeller, impeller with a blade not present. So, they all will have different characteristic frequencies. So, if I got such a signal from a machinery where all these components were there, and if I can find out the characteristic frequencies of the defects, I can pretty well say, well, the defect has occurred, because I see that frequency in the signature obtained from this machinery. Very simple to know. You have the students' roll list and you ask everybody to sign. Those who are present, they will sign. So, you will know in this class these students are present. Similar to that, if I know everybody's signature beforehand, and if I do a signature analysis and if I see the frequency components showing up, I can pretty well say, well, perhaps this defects occur, because their characteristic frequencies have come up in the analysis which I have done. Okay. Now, let us see how we do such analysis. For example, I have just explained to you before that this is a 10 hertz pure tone, because the time taken from 101 minimum to the next minimum is about 0.1 seconds, exactly 0.1 seconds. Okay. And if I take the inverse of this, I will get its frequency, 10 hertz pure tone. In an oscilloscope, if I get such a signal, I can just take the inverse of the time period and then find out the frequency content of that signal. But if I do the spectrum of this pure tone, I will get what is known, and this is in frequency. So, I will get a peak at 10 hertz. Okay. If I notice this had an amplitude of 10, whatever the unit, 10 volts or 10 whatever mechanical units. So, this is its amplitude. I know its time period. So, in the frequency domain, once the analysis has been done, I also see a 10 amplitude and also frequency of 10, because this is 50, and if I can divide it by 5 times, this comes to 10 hertz. Okay. Now, we will take it a little forward, in the sense, if I have just added 2 sinusoids, it will be very difficult if I asked you what are the 2 frequencies present in this signal. Some of you may estimate and do a correct estimation, but now imagine today it is 2 sinusoids, tomorrow it could be 30 sinusoids, 50 sinusoids. If I sum them up together, you will have a signal which I had just described, like the signal out of a real world machinery signal, and this is the problem we have in hand. So, a real world signal looks, in fact, even worse than this. It is not even as uniform and simple like this. Those of you who have done experiments in the lab must have seen this in the on the oscilloscope or on your analyzer. Okay. So, I have just done the analysis of this signal and I will show you this is what in fact it is. It is the summation of a sine wave of 10 hertz and with an amplitude 10 and another with an amplitude of 5 and a frequency of 50 hertz. So, if I have to write this signal, so the composite signal x t is nothing but 10 sine 2 pi times 10 t plus 5 sine 2 pi 50 t. Okay. So, if I just replace this as a sine omega t. Okay. So, omega is equal to 2 pi f. So, in this problem we have f, in one case f 1 is 10 hertz, other case f 2 is 50 hertz, a 1 is 10 and a 2 is 5. Okay. Just by comparison I have such a signal. Now, I could mathematically add many functions, okay, and then get up this signal. Okay. But in the real world signal, I have signal like this. If I can break it up into such components, I will know, yes, this frequency has f 1, f 2, f 3, and that is what we will be using the concept of Fourier analysis to find out the frequency components. Okay. We will first see for the case of signals which are well defined mathematically. That means they can be described by a mathematical expression or a function. Okay. Now, I had shown you the case when one was 10 hertz and another was 50 hertz. Okay. But if I add two signals 10 hertz plus a signal having 10.5 hertz, that means these frequencies are very close. Very close. Then what happens when the frequencies are close? A phenomena, the resultant amplitude looks something like this. That is, the amplitude suddenly increase, decrease, okay, and this is known as the signals are beating or beat phenomena has occurred, where the signals are independent of each other. Okay. Now, I will give you an example. There are ways, Fourier series is one method of estimating the frequencies of the signal, but there are other methods to find out the frequency of the signals. Okay. One such method is what is known as by signal heterodyning. I will pose you a problem in the case, in the sense, suppose in this signal one is 10 hertz and another is 10.5 hertz. I slowly bring by a frequency where I have a provision that I will have a frequency oscillator or a generator wherein I can change the frequencies, and I have a meter which is observing the amplitude of this meter of this signal, resultant signal. So, when the frequencies of this matches with this 10 hertz, this amplitude is going to be steady, is not it. So, then I will say that the frequency of the unknown signal is equal to the frequency of my known signal. Let me explain to you in this method. Suppose I have a signal S1, suppose I have a signal S2, where is the S2's frequency is known to me, and I have an okay. Well, this is the unknown signal. Now, my problem here is to know the frequency of this unknown signal. Okay. I have another signal which is my reference signal, whose frequency is known and whose frequency is set by me. Right. So, if I was to, if these two frequencies were well apart, I will be having certain frequencies here. But once they come close to the unknown signal is close to this frequency, what is going to happen? I just told you this beating is going to happen, right. Okay, signal is going to reduce in amplitude with time. Okay. Now, once the unknown signal's frequency matches with the known signal's frequency, this is going to be a steady amplitude. Okay. So, this will be a steady thing. I will relate this to, in the earlier days, people use transistor radios. Okay. When they tune the transistor radios and when they change the frequency setting of the station, when they came close to the frequency of the station, you will hear kind of a noise like waning and waxing, wow, wow. Okay. And then finally, it will catch on to ye Akashvani hai. Okay. Because it has latched on to the, because the frequency which you are setting is equal to the frequency of the received signal, and then they will match, and then you will hear the clear voice. But once you are very close to the station while tuning it manually, you will hear this signal which is waning, waxing because of the beating. Okay. And earlier days, when people were not having Fourier systems, where they are not having fast computers, they were tuning the frequency of the, because one frequency is known to you. So, the unknown frequency, if it matches, there will be a steady amplitude. Okay. And this is what is known as signal heterodyning, and I will show you the maths behind this. And this is what happens. For example, when I have the signal 2 pi f naught t and it is very close to f naught plus delta f, okay. And once this two frequencies match, delta f becomes 0, it is okay. And once this becomes 0, I will have, because delta f is nothing but f 1 minus f naught. So, this will become 0 and whole things will disappear, and then I will have a steady amplitude, okay. And this is known as signal heterodyning. to know the signal of an unknown signal by matching it with the signal of a known signal. I hope this is clear to all of you. Okay. And this is just from the trigonometric functions, but mind you, the signals are independent of each other. If they are dependent, they will modulate, and that is something we will discuss later on in the classes. But beating signals, because the known signal and unknown signal, they are independent of each other. Okay. I have a set of known signal, some unknown signal is coming, I am summing it up and then seeing this resultant signal. Okay. So, if I just add two signals, this is the, from trigonometry, this is the sin A plus sin B formula has been used here, and I will get this relationship. Now, another way of finding out the frequency, because I am telling you certain tricks which are used without even using Fourier analysis, and one such is heterodyning, another one is comparing the signals. If signals, if you do this if the signal is the two signals are the same frequency, this is if one is in the x axis, other in the y axis, I will get a plot of like this. If one is the twice of the other, I will get such figures, and these are known as Lissajous figures, and these are mostly used in orbit analysis. By this we can find out the relative ratios of the frequency of the signals. Okay. Now, before I come to Fourier series, there is another method by which we can do is set up filters. This could be analog in nature, in the sense, what is a filter? Filter means it will allow signals of certain frequencies to pass through and not pass through. For example, if I do the frequency response in frequency domain, this is how typically the response of a filter looks like, and this is known as 0 dB. This means logarithm of output by input. Okay, it could be log 10. When output is equal to input, what happens? It becomes 1, and log of 1 to the base 10 is 0. So, this is known as 0 decibel, and this is the typical frequency response of a filter. This is a band pass filter, wherein it has a lower limit f of L, and this is an upper limit f of C or f of U, and this is known as the lower cutoff frequency, and this is known as the higher cutoff frequency. Okay. Now, an ideal filter, what would happen in an ideal filter? This should be very sharp. Okay. But this does not happen, it takes certain other frequencies, because this is known as the filter roll off, and this depends on the order of the filter. I mean, I can have a sharp filter, sharp band, or a steep, depending on the order of the filter. We will not discuss this in details, but such filters are available in the market, wherein I know the lower frequency and the higher frequency. So, if there is an unknown signal, frequency is not known, I will pass it through a filter set wherein I know the f lower and f upper, and if I get some signal, I know that this signal is devoid of, or this signal has only the signals in, or I can look into them in also in time domain. This is all in time domain. This means that the frequency in this is between f upper minus f lower, and this is the frequency bandwidth. Here all frequencies are present. I do not know what they are in stage 1. I pass them through a filter in stage 2. In stage 3, if I get certain signal, I know the frequency of this signal is only between f upper and f lower, right? No problem. All in time domain. I need not know what the exact frequencies are. Well, question is, now if I want to know what the frequencies are, I can make this bandwidth very, very small. I can put a series of filters with very narrow bandwidths, isn't it? So, I can put a series of narrow band width filters, and if I know each one's bandwidth, I will see what are the frequencies which are present or not just by monitoring the amplitude coming out of this frequency of this filter set. So, I can have a filter set wherein these bandwidths could be tuned, they could be digitally programmed, they could be operated through a software, they could be set manually. So, there are many ways by which we can do that. Traditionally, when the computers were not available, people used such analog filters. Very broadly, the analog filters were used. They would manually tune the frequency of this filter set, see the amplitude at the output of the filter set. But nowadays, there are computers where we can vary. In fact, this bandwidth could be as low as 0.01 hertz, very fine resolution of 0.01 hertz. Next is 0.01 plus 2 into 2 into 3 into 4 into 5, and then I can have series of such digital filters. Okay. And this could be done very serially, okay, one after the other. But this, as you will see, will be very, very time consuming, and it cannot be done in real time, and there are problems associated with it. Okay. Nevertheless, filters can be used, analog filters, digital filters, to do such analysis. And while I am on the subject of filters, I should tell you about few other filters and how their responses looks like in the frequency domain. Traditionally, we will be using about 4 types of signal. A signal of filter of this sort, this is the response of the filter. Another could be another we just talked about, and another is or I am sorry, this one is the other way. In fact, please make a correction. Okay. So, this is, as you will see, is known as a low pass filter. That means, this allows the low pass frequencies signal to go up, and then after certain frequencies they are cut down. Okay. Because by using such a low pass filter, I can know that no frequencies beyond this cutoff frequencies are present in the resultant signal, low pass filter, and opposed to this is known as the high pass filter. That means, every frequency beyond the high pass frequency are available, are allowed to pass through, and this is, as you know, the band pass. And this is, it will kill a particular frequency, and this is known as a notch filter. Notch filter, I will just give an example. For example, in many of the electrical circuits, we have a predominant frequency of 50 hertz. So, if I put a notch filter of 50 hertz, it is going to remove that 50 hertz signal from the actual signal. So, this is where a notch filter is used. So, if I have such filters, I can also have an estimate of the frequency response of the signals. Okay. Now, we will look into the another theory behind frequency domain analysis, and that is what is known as this Fourier analysis. And I am sure this is a very important analysis which is used in engineering. In fact, mathematicians say that out of 10 great inventions or discoveries in mathematics, Fourier series is one such analysis. Fourier series has lot of engineering applications, be it engineering, be it mechanical, civil, electrical, be it in medicine. Everywhere Fourier analysis is useful, in the sense that the most important thing is anything, I will say what this is, anything can be broken up into its frequency components, be it signal, be it physical dimensions, be it the surface roughness. They can all be broken up into different sums of sines and cosines. Okay. And that is why this signal is this is very important. So, let us go back to how to determine the frequency spectrum of periodic signals. Now, as you all know, what is a periodic signal? Signals which repeat with time, and Fourier series says that the signal has to occur from plus infinite to minus infinite and periodic in nature. So, such a signal y t, where y is in the time domain, can be broken up into components as a naught by 2 plus n is equal from an a n cosine n omega t plus b n sin n omega t, where n goes from 1 to infinite. There is another way of representing this, but we can't find out the components a n and b n by this integration. Okay, I will not go into details of this, but I will just tell you the fact that y t, to determine a n and b n, you will see from this equation y t has to be mathematically known to me. And then we have a serious problem here. The real world mathematical signal which the real world machinery signal which I measure, I do not know its y t. I cannot represent it in a mathematical expression. If I was able to do it, represent it mathematically, I could very easily find out its a n's and b n's by doing this integration, and that is a problem. We will see how we can overcome this. So, this capital T is given by 2 pi omega is the period of the signal, where omega is the fundamental frequency or known as the first harmonic, that the fundamentally it is always known as the first harmonic, and twice of that is the second harmonic, and so on. And this you will find in any mathematics textbook, in your third year Fourier series or second year Fourier series, and this is the very generic form of such an analysis. I will not go into the details of such an analysis here, but I must tell you because of this Fourier, you can all make a note of it, and because I always find it, we should know about the great mathematician who has given us this Fourier series to us, John Baptist Joseph Fourier. You must have heard of the Fourier law of heat conduction, it is the same person. Okay. And we will see in this work he showed that any function of a variable may be expanded in a series of sine functions, a result which is frequently used in mathematics and science today and which we are going to use in this class. So, to begin with, if I have such an signal, okay, wherein its time period is t and amplitude is a, I can pretty well say, well, this signal has a frequency of 1 by t. So, if the signal is pure tone, I would be thinking that yes, very easily I can construct back the signal. Well, if I was to construct, I will only get a sine wave back, isn't it? If I just take the fundamental. But then I am not getting my original signal. My original, this is my original square wave. Okay. But then if I expand the Fourier series, there will be the other terms, and other terms are very, very important. So, if I was to take the definition of this Fourier, apply this on this square wave, and I was to estimate a n comes out to be 0, because the frequency is divided from 0 to t by 2. If I go t by 2, it is there is a typo here, this is not 1, this is t by 2. Okay. So, 0 to 2 by 2, this is a sorry excuse me, this is a, and t by 2 to t, it is minus a, the second half. So, this one is a and this one is minus a. So, I have broken up the signal into two halves, and then similarly if I do this, I will land up with a component of this form, a n is 0 and b n is equal to 4 a by n pi. So, square wave can be broken up into different components. Okay. And thus, if I was to represent a square wave in the frequency domain, this is the square wave which we originally had. If I did the Fourier series expansion by this expressions here, I will land up with such an expression wherein this is at the fundamental is at 4 a by pi, the second harmonic, in this case it is 3 omega, because the second one does not exist. So, it has omega, 3 omega, 5 omega, 7 omega and so on. So, a square wave x t can be broken up into 4 a by pi sin omega t plus 4 a by 3 pi sin 3 omega t plus 4 a by 5 pi plus sin 5 omega t and so on. And if I take these terms till infinite, if I add them up together, I will get back my original square wave. So, then with confidence I can say, well, I have broken up in this Fourier this square wave by Fourier series into its individual frequency components. So, a square wave is just not a sine wave, but a summation of such sine waves omega, 3 omega, 5 omega, 7 omega, so on. And I am sure in your maths classes you must have done such exercises for triangular waves. In your first year circuit, the teacher would have given you break up such a wave, periodic wave form into such Fourier components. Now, you notice interesting thing here. I have now put all of them together, all the harmonics individually they have been plotted, and eventually they have been added up. This is the sum of the first 3 harmonics with an amplitude of a is equal to 1. And you see this dark blue line, we have quite not got back the original square wave. Had I added more terms, of course, we cannot go up till infinite, but with large number of terms you will see that you will get back your original square wave. What this means is this square wave consists of frequencies of omega, 3 omega, 5 omega, 7 omega, etc. And so, if I get such a signal, I will know this is its frequency content. But the problem still rises that I do not know y t, and that is something we have to live with it. So, we have to do what is known as a mathematical or a numerical estimation of this signal and try to go from it. So, you will see the limitations of the traditional Fourier analysis, difficult to implement numerically for a measured signal, because one obviously has no obvious mathematical form and which we short. If I knew y t, I would have done this integration very easily got back. And another limitation of this Fourier analysis is it is limited to periodic signals. It cannot handle transient waveforms or random signals. For example, a signal which just occurs like this, I possibly cannot find out its periodic components because it is not periodic, and these are the limitations of Fourier series analysis. Okay. So, well, how do you go about it? There are the Fourier series, there is an integral method to do it, wherein instead of summations, I do an integration from minus infinite to plus infinite, and in such a way I can transform a signal from the time domain to the frequency domain by doing this forward transform. Okay. And we will see how this is done. And the vice versa is also true. If I have a signal in the frequency domain, I can get back its individual time domain components, and this is known as the inverse Fourier transform. Okay. When we have it in the integrational form, we call it as integral, or in the digital form, it will be known as the Fourier transform, okay, digital Fourier transform. Okay, and this can be all done digitally. Okay. But in order to do this Fourier transform, I need to have a representative of the signal, okay. And the Fourier transform or integral, this y t could be anything, may be transient, could be random, could be periodic, okay. And the Fourier transform is a complex quantity, okay. And then we always have a Fourier transform pair, wherein the signal can be related from time to frequency or frequency to time. So, we have this Fourier series, which is for periodic function. We have the Fourier integral, transform, which can be for non-periodic and the random signals. And then if you look back here, this integration could be done numerically. Once I do numerically this integration, I need to have an estimate of the signal y t at every numerical steps. Okay. So, to digitally implement the Fourier transform, I can call it as digitally implement Fourier transform, or sometimes it is known as discrete Fourier discrete Fourier transform or DFT, I need to have digitally acquired time data. Then this integration can be done. I will. So, the problem is now how do we get this digitally acquired data? I have a signal which is occurring like this. I want to do is DFT, so that I can get the frequency spectrum, but then question is how do I do DFT? Well, there are many algorithms to do DFT, we will discuss that in the subsequent classes, but most important is I need to digitally acquire the time data, and that is known what is known as the computer aided data acquisition. Data has to be acquired by a computer, converted from analog to digital sample data. This is a real analog data. I have to digitally sample them, so that this digital data YKs can be put in the DFT algorithm to get the Fourier spectrum. Once such Fourier spectrum is obtained by us, we can see how this analysis can be done. Okay. So, as a homework, I could ask you to try out the Fourier series of find out the Fourier series representation of these signals. You can take them as A, and this is t by 2, and this is going to infinite. This is a triangular wave. Another is you could have t by 2 t a, okay, a positive sided square wave where the negatives are chopped. You can find out the Fourier series expansion of such waves. This could be a homework for all of you to do. Okay. And we will either put the results in the website, or we will discuss that in the subsequent tutorial classes, this lecture. Okay. So, in the next class, this would conclude this lecture on the frequency domain signal analysis, but we still do not know how to implement this with real world signal. But the problem I have posed to you is we need to acquire this analog data into a digital form. Once this data is there, there are many algorithms which we will be putting in to find out the frequency estimate of the signal, and we will discuss that in the subsequent classes. Okay. Thank you.